Good afternoon, everybody. My name is Richard Moorhead. I'm from the Faculty of Law. I'm here to just chair today's proceedings, so I'll just be keeping everybody to time and shooing people out at the end because there's a lecture coming in straight afterwards. It's my real pleasure to be able to kick off the series of lunchtime lectures and to welcome Dr. Steve Fossey from the Department of Physics and Astronomy and some of his students in the front row who together discovered a thermonuclear supernova in our cosmic neighbourhood. None of those terms I understand, so I look forward to hearing the lecture and to hearing some of your questions at the end. Thank you very much.
Thank you. Okay, well, I hope you can hear me. Can you hear me okay at the back? Good. Okay. It's been rather a ride, really, since January. This has been... I'm going to try and tell you something of a personal account of how a myriad set of circumstances conspired to cast what is actually a jewel of a supernova across our path back in January from a sleepy corner of northwest London in Mill Hill, which is where our observatory, where UCL's observatory is based, and which we've come to realize is potentially such an important object in helping us understand some of the most fundamental problems facing physicists and cosmologists today. So if I've learned one thing, it's that there seem to be two ways to discover supernovae. The first way is that you look for them, and the second is you don't. And my method, I seem to use the second method, but in so doing, I'm actually in extremely good company. If we go back in history, we find that there's a whole host of distinguished astronomers who discovered supernovae by not looking for them, including Tycho Brahe, who in 1572 was, it seems, on his way home from, well, what he called the alchemy lab, sounds like a euphemism for the pub, and saw a bright light in the sky up in the constellation of Cassiopeia, a very familiar W-shaped constellation in the northern sky. And here, in Cassiopeia, outshining all those stars, was a new bright star that he had never noticed before. And he wrote this up in a note, De Nova Stella, in 1573. And actually, he performed some very important work because he made some fundamental measurements of position of this star and showed that it didn't change in position, which was contrary to the moon and planets, which could be observed to have a parallax and were therefore closer than this object. And so he challenged the philosophy of the time, which was that the heavens were unchanging in the realm of the stars, because here was a change that had taken place. Now, this lasted for about 18 months in the sky and was visible during the daytime. It was so bright. And it was followed not long afterwards, in fact, by his successor, Johannes Kepler, just a generation later in 1604 in October. Sorry, this illustration isn't so clear, but down in the foot of the constellation of Ophiuchus, just here, one finds actually there was a conjunction of three planets, which itself was significant in the understanding of those times. And then within that, a bright light appeared, another supernova, within just a generation of Tychos. Well, you then really have to wait for about 400 years until we see another bright naked eye supernova, which is visible from Earth. And in 1987, Ian Shelton, who was an astronomer working in Chile at an observatory there, was developing a photographic plate and realized there was an enormous bright new object on there and stared at it for about 20 minutes. And in the end went outside and realized there was a new star, what appeared to be a new star in the sky, supernova 1987A. You'll see the interesting naming conventions. We just give a year and a letter designation to these things. Well, this was in the Large Magellanic Cloud. Now, the Large Magellanic Cloud is a satellite galaxy to our own, so it's not really within our own Milky Way, as Kepler's and Tycho's supernovae were. It's really, if you think of the Milky Way as your own house, then this is in the garden shed. But it was the closest bright supernova that we'd had for 400 years. Typically, a supernova we expect to occur about once every 100 years in any given galaxy. And there have been a couple within our own galaxy, probably since Kepler's, but which have been embedded and therefore very, very difficult to see, being hidden behind dust. Just going slightly back further in time, there was the observation of another bright light in the sky, this time by Chinese civil servants who were working for the imperial court in the year 1054 AD, and their job was to monitor the skies for any unusual happenings. And they found a bright object in the sky, recorded it, and it was later observed in the modern telescopic era in the 20th century, and this was discovered. This is the so-called Crab Nebula in the constellation of Taurus. And the material within the crab represents the end state of such a star. This is what this and Supernova 1987A are the end results of what we call core collapse supernovae. And those supernovae result from the fact that a star lives by fusion processes. It fuses hydrogen in its core into helium atoms, and those helium atoms then get cycled into carbon and nitrogen and oxygen and so on. And in very massive stars, stars about 10 times the mass of the sun or more, that process will continue right up until you form iron. Now, iron can't fuse any further and deliver any more energy to sustain the star. So when it gets to that state, it very rapidly collapses in on itself, and the outer layers effectively rebound off the core and blow themselves out again in a huge shock wave. And this is what we're seeing some 1,000 years later, is the remnant of this enormous explosion. And this is, we're seeing heated dust grains, and we're seeing the gas which has been come from the star itself, but also new elements which have been formed within the supernova explosion itself. So elements higher than iron are formed by the capture of subatomic particles called neutrons. So all you have to do is the ring on your finger, the gold comes from most likely supernovae such as this one. Now we know, you know I'm sure, that this is the story, we are made of star stuff. The process of star birth, death, and regeneration of new stars is fundamental to our understanding of the formation of the sun, the earth, and you and me. We are formed from the ashes of stars. This is an illustration, or a picture actually, of the constellation of Orion, but it's on its side. You can see Orion's belt here. Here is Betelgeuse, a red giant star, many times more massive than the sun, that has reached that late stage of evolution. This will become a core collapse supernova, but we just don't know when. It could be tomorrow, or it could be in 10,000 years' time. But when it does occur, this will be bright. This won't be discovered by any astrophysicist. It'll be you walking down the street saying, what's that thing in the sky, along with a few million other people. But the material from this process of star death gets recycled into, there's some new stars which are forming here. Can we dim these lights a little, or not? The ones above me. There are new stars which are forming here in the Orion Nebula. And these new stars, so the process of the chemical enrichment of the galaxy is fundamentally understood by our observations of such supernovae. Well, how do we understand the chemistry? Well, if you go back to your recollection of chemistry, you know that when you put different elements into a flame, we see different colors. And here we have copper in green, sodium in yellow, strontium in red. These are the signatures of different elements within the gases that are being that we're looking at here and we're providing energy to. If we were to attach a spectrograph to such an experiment, we could split the light up into its component colors, and we would see the same thing and uniquely identify elements within the gas. Now, if we do this with supernovae, what we find is that broadly around the 1940s, it was recognized there were two types. The so-called type 2, or the core collapse supernovae, have a very, very strong emission from hydrogen gas. Now, that's not surprising because of all that hydrogen that's sitting on top of the core at the moment of collapse, and it gets blown off. But it was also found that there were some, the so-called type 1As, which had no hydrogen at all, which is very strange. Instead, they were characterized by a very strong line formed by silicon atoms. So where's all the hydrogen gone? Well, the clue is actually very close to home. Our own sun, which is 75% hydrogen, will end its lifetime in about 5,000 million years' time by ejecting the envelope of gas and leaving at its core what we will come to call a white dwarf. And this white dwarf is effectively the dead nucleus of the star which was, having fused hydrogen to helium and then helium perhaps through to carbon. This process will occur for stars typically of the mass of our sun, and those a little more massive, up to say about 8 solar masses. So we're left with a white dwarf star for a star that may have started off with 5 solar masses, about the mass of the Sun, but in a volume about the size of the Earth. So we're talking, the Earth is, there are 109 diameters of the Earth across the Sun. So this is an incredibly compact and dense object. And in fact, the state of the matter is, we call it degenerate. The electrons are in a particular state which is not described anymore by normal physics, at least normal classical physics. And this was realized, in fact, by a brilliant young Indian mathematician called Chandrasekhar, who, on a boat journey in the early 30s to Cambridge to come and study astrophysics, realized and did a calculation that such objects could not exist if they had a mass greater than about 1.5, just a bit less, 1.4 times the mass of the Sun. The physics would not permit it. So here would be a natural explanation for producing a type 1a supernova with no hydrogen, no helium gas. But of course, how do you get such a dead star to explode? It can't explode on its own, so what it needs is a friend. And if it has a friend, then it can start to draw down matter from that star onto itself, and we basically have a recipe for a nuclear bomb. You take one white dwarf, less than 1.4 solar masses, you start feeding it hydrogen gas, and when it reaches the density and the temperature in the core reach a critical state where the carbon atoms will fuse with oxygen and produce heavier and heavier elements up to, in fact, nickel, and this blows the star apart in a runaway thermonuclear reaction. This destroys the star completely. Remember, this is an object the size of the Earth, and it is gone in a few seconds. It is completely consumed by this explosion. Well, the process by which this occurs, the accumulation of gas, and then the explosion produces a large volume of nickel. An explosion like this produces about 200,000 Earth masses of nickel atoms. But these nickel atoms are radioactive, and they decay quite rapidly within a week for about half of them to cobalt. The cobalt is also radioactive, and it decays to iron. Now, the iron, these supernovae contribute about 3/4 of the iron in the universe, we understand. So 3/4 of the iron in the hemoglobin in your blood and mine comes from supernovae like this, in quite a literal sense. Type 1a supernovae are the reason we live and breathe. And it's these decay reactions also that produce actually a copious amount of gamma rays. Gamma rays, very high energy radiation, which actually heats this expanding shell of gas and causes it to glow. Without the gamma rays, we wouldn't see it. And these are enormously powerful explosions, as you can imagine. And if this movie will run, here it goes, you will see that in distant galaxies, it was realized that these objects can brighten to outshine the sum total light of the individual stars within those galaxies, about 5,000 million times the brightness of our sun at its peak. And we can map this variation, this brightening and fading, and we find that actually it proceeds in a fairly regular way. Here we see actually a sample of many, many different types, many different supernovae. But one can calibrate these by looking at the rate at which they fade away, and it turns out that they become very, very consistent in terms of their peak brightness. So this is what we term in astronomy a standard candle. We can now use these things as a standard way in terms for measuring, for example, distances to remote objects. And this was done in the, I'm going to skip through a couple of slides, this was done in the 1990s in particular, aggressively through the development of technologies actually which relied on silicon, that is telescope mirrors, computers, and detectors, which led to a plot which we don't fully have time to discuss, but basically when we look back across the universe, we see objects which are moving away from us faster and faster. This is what we might call a version of the Hubble diagram. And those which are further away are fainter. Now, if the universe were expanding at a uniform rate, then we would see these points lie along more or less a straight line in this diagram, but actually they curl upwards. And this is an old plot, but this has been validated many times since. And what is happening here is that rather than the universe expanding at a uniform rate or even slowing down as we might expect it to, it's accelerating. There is something else going on here that is new in physics, which has come by cosmologists to be called dark energy. And the phrasing as much reflects our understanding of exactly what it is. which is very, very little. So this is a fundamental observation. The accelerating universe is established. We don't know what dark energy is, but there's a tremendous amount of work being invested to try and understand what's going on. For this work, the authors, the leaders of these teams were awarded the Nobel Prize in 2011. So this is very, very forefront physics that is going on. And a great deal of investment has gone on to try and find many, many more supernovae. This is the supernova discovery rate per year for about the last 15 years, last 20 years. Currently standing at about 2,000 supernovae per year. As this whole process has been industrialized and telescope systems are monitoring the skies continuously to find these objects. Why? Because they can tell us something by measuring the expansion rate of the universe and pinning down the parameters that help us to understand and test what this putative dark energy is. It's telling us something fundamental about physics. There is a whole lot more work that's going to be coming on in the next few years through missions which are currently either operating or being planned, in addition to which there are amateurs such as this gentleman here, Tom Bowles, who observes the sky every clear night from Suffolk and has personally discovered over 150 supernovae by looking at images of galaxies in order to find them. So it brings us actually to a rather embarrassing problem, and that is that we don't actually know how the white dwarf explodes. This illustration is meant to just show you that there is a variety of theory, depending on the nature of the companion, that could actually lead to a white dwarf explosion, but we don't really understand what it is. By and large, the recipe seems to be the same, which is why supernovae are such good standard candles. Therefore, it would be really helpful if we had a local nearby supernova, type 1a thermonuclear. This is an event, actually, which took place in the year 2011. This is about 20 million light years away, this galaxy, which is really just up the road, not so far away. And there is an object here which will appear just here. And this is how we detect a supernova explosion in such an external galaxy, by detecting a new object, which was not there last night, last week, last month. So our observatory in Mill Hill, northwest London, comprises a number of different telescopes. We entertain a large variety of undergraduate students taking different degree courses here at UCL. We have some larger instruments, such as the Radcliffe telescope illustrated here, but a lot of the time we're also using some of our smaller 14-inch aperture telescopes, and these are operated from control rooms. So having set the telescope up, we would retreat to the control room in order to undertake our observations. Well, back in January, we had such an evening where students were observing, or planning to observe, because the afternoon had been clear and everybody was getting ready for their first observing session on the telescope. But around about tea time, it started to cloud up. And so the students were disappointed. Many of them were looking forward to a first observing experience on the telescope. They'd been doing computer-based work in the afternoon. And I did something actually that I almost didn't do, which is I said, well, let's go and do something anyway, because it can be such a disappointing experience. And we looked at the sky, and in the north, where there was a little gap in the clouds, we could see we knew of a couple of galaxies, so-called Messier 81 and 82, which were still visible. So we pointed the telescope and took a picture. This isn't our picture, actually. This is the Hubble Space Telescope picture, which is showing us, actually, it's such a fascinating and unusual galaxy, a so-called starburst galaxy, which is actually exhaling a tremendous amount of hot gas because of intense star formation activity going on in its core. Now, this is a picture that we took of that galaxy in December. And I want you just to memorize briefly, there is a pattern of stars, 1, 2, 3, and here's the main axis of the galaxy. And this is the first image that we took on that night. And this is just what we call a pointing exposure. It's the first shot just to check everything's working. And here's the galaxy not centered in the frame. And there are 3 stars, 1, 2, 3, as we saw before. But nothing really much else to take notice of. But if we look more closely, in fact, if we adjust the contrast on this image, you will notice that, in fact, there appears to be a new object right here. Now, this was astounding to me. I mean, this was a 10-second exposure, not very long. So we took another one of 70 seconds just to try and collect more photons, and it was still there. Now, I still didn't get too excited because I've seen weird things before. Here's a picture that we took some time ago of a crab, of an object. This is the crab. And there are what appear to be actually 2 new sources within this image. Well, we're on the flight path to Heathrow. And these are two strobe lights from a passing aircraft, which have left an image in the camera. There's these telltale trails, but which also can sustain themselves as ghost images in subsequent frames. But it was only when we recentered the telescope and this was still there that I thought, well, this is unusual because that's obviously real, or it seemed to be real. And the students and I, Guy, Ben, Tom, and Matt, who are here today, we kind of talked about it for a moment, and I said, well, look, we need more data, so you guys collect as much data as you can. They took a 2-minute exposure, and it got worse. And it got worse because there's more cloud. We're actually losing the sky at this point. So I run over to, on the other side of the observatory, just about 10 meters away, we have a twin telescope, and I set that one up, and after about 10 minutes, I take another exposure, and now just about, there's the galaxy, you can barely see it, just about pick it up again. So by now I think, well, this is not just a fluke in one telescope, it's now in 2. So it seems to be real, and the kind of thoughts that go through my head, it was quite evident to me there'd never been any star in that place of the sky so conspicuous and bright as this. And I doubted the trustworthiness of my own eyes. Well, who said that? That was Tycho Brahe. But this was exactly what was going through my head. This was weird. Nobody leaves these things laying around. You've seen the amount of effort that's gone into trying to discover and find these objects. So what's going on? Well, thankfully, the students themselves had no such reservations. They've already taken a supernova selfie. Here they are. This is Guy and Ben and Matt and Tom and the supernova just there on the screen to commemorate the occasion, and good for them. I'm glad they did. We had a number of things to do. Sorry, apologies for the maths, but we ran up to the classroom. I started to get slightly stressed because I thought, I don't really understand why this is not documented. We checked online, there's nothing there. We checked it's not too bright. If it's too bright, it can't be in that galaxy. It's not too bright. We checked that it's not an asteroid. There are databases we can go to. 500,000 asteroids were checked. No, it's not an asteroid. So it's starting to look real. So at 9:30, I dismissed the class and realized that I was going to have to write up a report, and you have to notify the community. Well, what do? Well, the first thing you do is you don't go onto Twitter. There is a mechanism by which you can report these events in order at least to gain priority, and it's called the International Astronomical Union Central Bureau for Astronomical Telegrams. Now let me show you the instructions for reporting a supernova. There they are. Now that's a busy slide. It is a busy slide, and you're relaxed and having a drink and some lunch, and it's busy for you. Now I was rather stressed at this moment, so this is what it says, but this is what I saw. I had trouble really just focusing and thinking, right, I've now got to respond to this amazing opportunity, but I just have to focus and actually get this report written. So one of my colleagues, actually, Stephen Boyle, checked my numbers and reassured me that actually I hadn't really blundered, but I still wasn't sure, and I checked and double-checked and triple-checked and sent my report about a few minutes past midnight. I was now on my own at the observatory to the Central Bureau. And then I realized that actually, a few minutes past midnight here, the Central Bureau is in Harvard, where it's 7 o'clock in the evening, and I was worried that this would sit in an inbox till the morning. I really needed to notify the rest of the astronomical community that something really important was going on in Messier 82. And they have, apologies for the busy slide, but again, they have a transient object confirmation page. So I think, well, this is good. What do I do? Well, what you have to do is prepare a simple line of text which comprises all the technical detail of. So this is like me trying to read a fire extinguisher when the house is already on fire. It's impossible to do. So eventually I just about get my mind together and do it, and then this is the designation that I was about to submit, and I discover that in order to submit to this page you have to be registered and you have to send an email. It's by now about 3 o'clock in the morning, and the phone rings, and I think this must be Dan Green, the director of the Central Bureau, getting back to me about my email. Hello? And it's my wife. She says, where on earth are you, and what are you doing? Because it's tipping with rain. She knows I'm not observing. So we have a brief conversation about that and try and sort it out the next day. But thankfully, God bless him, Dan Green, the Central Bureau, at 5 minutes past 3, he updated the confirmation page for me. And instantly, or within half an hour, astronomers, in fact amateur astronomers, this is a Japanese amateur astronomer who was using a telescope remotely in New Mexico in the United States, obtained a confirming image. So now we know it's not just over Mill Hill in London. There's something really there, as well as other observers, such as Ernesto Guido and colleagues. But the key is actually to take a spectrum. We need a spectrum to verify if it is a supernova. It's going to show something, possibly a type 1a, type 2. We need to know. And here it is. And this was obtained by the Palomar Transient Factory. I had emailed them as well about 3:30 in the morning to say, this is rather interesting, could somebody get a spectrum? And there's the line of silicon that they determined at about 6 a.m. that morning from an observatory in the United States. So we now know, and they published online at about 9 o'clock, 10 to 9 the next morning, that this was a young type 1a supernova in the galaxy Messier 82. So this was good news, and I had a celebratory cup of tea after a couple of hours sleep. And then I contacted, it had the designation later on, Supernova 2014J, this lovely interesting designation. And I contacted Ollie Usher, who is our media communications in MAPS, and said we should get a press release out about this. And he said, oh, I know all about that, it's on Twitter. So, and I thought, I forgot all about Twitter. I wasn't even on Twitter, I didn't know how to use Twitter. And yet it already picked up and become a bit of a roller coaster in its own right. So Ollie, bless him, managed to get a photographer in, and here are the students, the reservoir dogs, the 5 of us, and looking as if we're ready to do a bank heist. In fact, they're down here at the front, should you wish to hire them for such a purpose. And I really can't praise them enough, actually, for this set in motion a roller coaster of media interest, including from Spiegel Online. And Ollie had asked our students, well, what does this mean? What do you think about all this? And they're brutally honest. And Tom, bless him, I'll just forgive my German if you're a native German speaker, but he said, and it says the headline, the strapline here is Supernova while eating pizza. Tom Wright beschreibt die absurde Situation. Vor einer Minute aßen wir noch Pizza und 5 Minuten später eine Supernova. Ich konnte es nicht glauben, I couldn't believe it. This was found soon after. They were having trouble getting it registered. Okay, I have 5 minutes and I'm really running behind time, so I'm going to accelerate up to some of the science, but I would like to just highlight, we were extremely lucky. Amateurs observed this in the days before we did, but it was not recognized. This is a British amateur who sent me a picture. He was glad he just found it. There was a group of amateurs, Fraser Kane, bless him, who's runs the website The Universe Today. They were having an internet discussion about the galaxy and didn't notice that it was there. He mailed me this morning, actually, I asked permission to use this. He said the irony of that situation is incredible. They really, I mean, total respect for them for actually reflecting on it in that way. This is a list, forgive the detail, but there is a website which you can follow if you wish, which lists a lot of pre-discovery observations before ours. There are at least a dozen amateurs who found this. And the professional surveys, I'm going to have to race through this slide, so I apologize, but the Palomar Transient Factory, which operates out of California, this is a sheer fluke. You couldn't make this up. They missed it because they're looking at this galaxy almost every night. Now, what happens is, on January the 16th, there is a full moon. So on the 14th of January, they switch to a different mode of imaging, which suppresses the image of the supernova, which we now know occurred on the evening of the 14th. By the 20th, they switch back to their normal mode of observation, and it's too bright, and it overexposes in their image, and their computer software does not recognize that it's there. That is an absolute fluke. Meanwhile, over at the Lick Observatory Supernova Search, they actually had it, and they had it in several data, and you can see it appear in this animation of images. There it is. It appears around about the night of the 15th or the 16th and brightens. But it wasn't detected by their software, nor by their volunteer checkers who would look at some of the images the next day. So we were extremely lucky that this was still on the table. What they did do, however, was they acted extremely rapidly to put together some brightness measurements. And forgive me for the detail, but this is the rising brightness curve, which shows the thing brightening up over the days after January the 14th. 0.75 is around about when we think it first brightened. And it brightens even more steeply than some of our physical models permit. So there's something new and unusual going on. This is the second known supernova to be behaving in this way, which is telling us something about the explosion mechanism. Now, if you were to do an experiment, maybe just once, you could blow up your house and observe what happens as it falls apart. That would be a way, an expensive way, to try and do an experiment to see, okay, what was the structure of my house? You see the walls moving towards you, then you see the sofa and the TV, and they are being affected by the explosion in the process. This is exactly what we have here as a model of an explosion of such an object. And down in the heart of this supernova is the nickel which has been generating. And in the outer layers is material that's been cast off before the nuclear fusion has got a hold of it, carbon and oxygen. So by doing an autopsy on this object, we hope to understand something about the explosion mechanism, and it's these techniques that we can apply through the use of spectroscopy, as we've discussed. And this is a time series which shows the changing evolution of the chemical makeup, and we look deeper and deeper and deeper into the heart of the supernova itself. This work is now being done, and there's new data coming out almost monthly to do this work to understand exactly what the mechanism is. NASA put out a press release to say that a vast array of their instruments were going to monitor this object, and indeed they have been doing. This is an arsenal of equipment which is being used in order to try and resolve this question. What is the origin of the progenitor? What can we tell? Well, there are different kinds of observations that can be made, and I'm running hard against time, so I probably won't be able to tell you about all of them, but one of them is you can do some galactic archaeology. You can look for, in images that were taken, these images of the galaxy were taken in 2006 by the Hubble Space Telescope. So why don't we look there and see what was in that location? Well, it's extremely challenging to do, but you can try. If you concentrate on the middle panel here, within the red circle, is there anything to be seen? Well, apparently not. And what this tends to do is rule out the biggest companion stars. It means it has to be something smaller. It can't be a red giant star that's doing this. This is a very important observation from a gamma-ray observatory, which for the first time ever for this type of supernova has detected the gamma rays from the radioactive cobalt at the heart of the supernova. And this is telling us something. It confirms what we really always expected, but it's also telling us something about the process itself. And then if I skip forward, there are two further observations that in fact are critical. One is to observe the region with radio telescopes, and this is that observation. And I hope you'll agree with me that apart from some ripples in the background, there is nothing there. And if you observe also in the X-rays, you find there is nothing there. Well, what does that tell us? Well, this process by which the material is dragged off of these companions is a very leaky process. Gas goes everywhere. And over the millions of years over which this occurs, we expect the progenitor system to be surrounded by that gas. And when the explosion occurs, it impacts that gas and it accelerates electrons that you then see producing light in the radio and X-ray. If it's not there, it tells us that the environment around the supernova, possibly representative of the white dwarf scenario, is relatively clean. The average density of that material is a few particles in every cubic centimeter, which is about a million times less dense than the air in this room. So what it's telling us is this scenario is definitely ruled out. This one almost certainly is, most scenarios there. It's telling us more and more, the evidence is pointing towards the one remaining one, that the merger of two white dwarf stars is the primary candidate scenario. For this one, it doesn't mean that every supernova that we see is, but it gives us one case study now, close enough, the first that we've had close by for 400 years, since Kepler's supernova, which was a type 1a. So what's remarkable to me, as we just pan through the last few slides which show us the transition between these different wavelengths, is that this object, which has such an intimate connection with our own animal humanity through our blood, and yet also with the investigation of deep new physics in the expansion of, measuring the expansion and cosmic history of the universe, that all of this was triggered by actually a rather cloudy evening in a sleepy corner of northwest London. Thank you very much for your time.
We've got maybe 2 or 3 minutes for questions, either for Steve or for the fellow discoverers.
Yeah, thanks. Great lecture. Does this have any relevance with nuclear power generation? And why are we making dirty nuclear fuel when we could be making nuclear, I'll get it right, is it fission or fusion, the one that's clean?
It doesn't have any direct relevance. We've always known that fusion of hydrogen, if you can do it, is cleaner. It's a cleaner process. It does generate its own waste products. But yeah, it's extremely difficult to do. I mean, you can see it can be done in the sun. Doing it on the Earth is a very difficult process, but I can't comment further.
Yeah, thank you. Why does the reaction seem to stop at iron, or then you mentioned nickel, then cobalt? Is it just a question of the number of electrons in the shells?
It's to do with the binding energy of the nucleus. You can't, when you fuse elements, say you fuse hydrogen together to form helium, you actually end up releasing some energy in that process. There is a mass deficit, and that mass, in fact, through Einstein's equation, E equals mc squared, tells you the mass is generally converted into a form of energy through photons. But that stops at iron. It has an iron and nickel, the iron group, have the maximum binding energy and produce no more advantage by the fusion process. The only other way then is through the build-up through neutron capture, which can happen in some old giant stars, but it happens very rapidly in supernovae to build up the higher elements that we know about, all the way up to the top of the periodic table.
With the model of the type 1a supernova, there's a star with a companion white dwarf. When the white dwarf goes kaput, would there be any evidence that, what would happen to the companion star? Would it get shredded? Would there be
it's a very good question. We expect it would survive, actually. And of course, if these two things have been going around each other, then when this one is gone, it carries on. It's like falling off a roundabout. It just keeps going, okay? We expect it survives. Its atmosphere, its surface layers may get affected by the explosion. There are ways that one can try and see it after the explosion, but for many supernovae, type 1a supernovae, where this has been attempted, it hasn't been found. And again, that's another pointer that maybe we are looking at more low-mass companions or even the white dwarf companion. So the evidence seems to stack against the larger. It doesn't mean in every case. We know that there are cases of the large giant star in a binary. We know about those. We have some in our own galaxy because they produce flashes of light every few years. They're called recurrent novae. But for the most part, the type 1a supernovae, we see no evidence of the companion in the searches that are done. But it does survive.
One more question. At the back. Yes.
Where can we go to hear the full version of your talk? It's such a fascinating thing.
Okay, I don't know. This is an hour talk that I scrunched into half an hour. You'll have to forgive me for racing through parts of it. I'm giving a few talks to astro societies, astronomy societies, and so on. Maybe I should post something online and somehow disseminate to. I'll try. I put my. Do you go on Twitter, sir? I'm on Twitter now. I don't know what to do, but I'm on there. Maybe I'll post on Twitter when I'm going to give a talk. You take out an account, and you can see where that's going to be.
All right, thank you. Steve, that was absolutely fascinating. Ladies and gentlemen, thank you.